All right. Again, hello everybody. Let's get started with the talks. The first up is Peilin Ye. Peilin, you want to go ahead and share your screen?
Yeah. Can you see it?
Yep.
Okay.
You can start whenever you like.
Hello everyone. I'm Peilin, and my project is about multi-vertex trigger, and the full name is Machine Learning Pileup Suppression Trigger Algorithms for the High Luminosity LHC, and I'm working with Dr. Ariel and Dr. Rainer from Slack. And I'm a rising senior from University of Pennsylvania, and I am now considering applying for a PhD next year. So the motivation is that at the high luminosity LHC with like roughly like 200 collisions per event, there will be a really much higher intense pileup rate comparing to what we currently have. So you can see the plots below. So now the majority events have like one hard scatter, one hard vertices, but then in HL-LHC, we expect to have an average about like 2.2 hard vertices. So for the HL-LHC, really telling that how many hard vertices in each event will be really helpful, especially, for example, distinguishing events that are 4-jet from one hard scatter, or like there are 2 dijet hard scatters. And so we aim to use machine learning algorithm at trigger level, like eventually at trigger level, to tackle this issue so that we can, using that trigger, we can save more interesting events that we're curious about, and we can use it along with other cuts, other triggers to help us select events. And the plan is to first prepare the sample that's already been done. So the green is what I've done, and the red is what's doing. And so we start with samples that are DODs, and then the first thing to do is to process them into n-tuples for easy access and easy machine learning access. And then we use delta R pairing to pair reconstructed jets with truth jets, like hard scatter jets, or in-time pileup jets, out-of-time pileup jets. And then for that paired reconstructed jets, that will eventually form our training set. And we will use the pair information to tag each event, like we'll talk about that later. And then after getting the training set, we will train the model and considering the trigger level restrictions, and then the possibilities of implementing the model on a FPGA eventually. So first thing is sample preparation. So one thing interesting happened is that we noticed that the DAOD file haven't gone through the jet quality filter. So I dig into the files and apply the tile gap 3 to kind of filter out those weird jets with a specific like peak on some specific eta. And we collected the 4 vectors, the width information, the colorimeter width, and the z position for pileup jets as the information to form the n-tuple we use. And then we do jet pairing on the n-tuple, so we use delta R pairing. So we match, so in each event, we match each reconstructed jet to a truth jet that is the closest with it in delta R. And we also require that a max PT ratio, which refers to the PT ratio between the truth jet and the reconstructed jet, so that um, each truth, so like for each reconstructed jet, at least um, no, for each truth jet, no, for each reconstructed jet, at least half of its PT is from the matched truth jet. And so this is a result when we're using one slice from the JZ2 slice, which is referring to the events that with the leading jet PT is between 60 and 160 GeV. And we have roughly 20K hard scatter, roughly 20K stochastic jets, which are jets that are not paired to anything. We have 14K in time and some of out of time pileups. And we can see from these plots how well the jet matching is. So the first one is the delta R. So we see that for hard scatter, we do a pretty good job. And also for hard scatter, the PT ratio is clustered at 1, which is expected. And then we did something called stochastic jet removal. Well, the motivation is that first, they're not really jets, they're just noise, and it's just because of random soft clusters just happen to be at one place in the colorimeter so that it get catched as it get reconstructed as a jet. And also we see there's a lot of stochastic jet, especially at low PT. So the greens are the stochastic jets. And so removing this will help the model to distinguish between what we actually want to distinguish is like jets that are from different vertices, which in this case hard scatter jets and in-time pileup jets. And from this width, his histogram, we can tell that we can just apply a simple width cut to filter out some of the stochastic jets. Actually, a lot of the stochastic jets. And this is the result. So I've used, so we just used width as the cut, and we have two ROC curves. So each apply to one region on PT, so 30 to 40 and this 40 to 60. And we can see that we do have some discrimination against stochastic jets. For example, at this point, we can accept 80% of in-time and in-time pileup while only accepting 40% of stochastic jets. And on these plots, our efficiency, well, this efficiency is about hard scatter jets. So when we had 90% of hard scatter jets, and this is for the 30 to 40 spin, so we use that as a global cut. And this is the number of jets per event with PT more than 30 GeV. So we can see for this efficiency, we lose some of the stochastic jets and not much lose on hard scattering in time. And for this efficiency, we lose more stochastic jets while slightly hurting the hard scattering in time. And this one is kind of a similar idea, but we plotted the x-axis as the hard scatter jet efficiency versus the number of jets above actually above 30 GeV per event. So we can see that for large regions, we are having the power to remove quite a lot of stochastic jets. And I believe this will help us in training stage. And I also made a pretty event display that's actually 3D and is actually interactive, but here's this on the slides. I can only do a screenshot. So this is one very good performing example. So we can see that before we have all those reds are stochastic jets and blues are hard scatter. The purple one is out of time, so we can see that we actually did a quite good job doing the width cut. And the next step will be package events. And we want to start with like events with 4 hard stack jets versus events with less than 4 hard stack gathered jets and some in-time pileup jets. Then we will train the neural network model using 4 vector and width. So not any other informations, as the 4 vector and width are the most accessible information at trigger level. And we'll also consider trigger level hardware restrictions and also optimize for FPGA implementation. And yeah, if possible, I want to explore actual implementation on FPGA, but that depends on time. And this is all I to share so far. Thank you.
Thank you, Peilin. Any questions? Gordon?
Yeah, that's a oops. Rob, could you mute? Yeah, there's a pretty bad echo. Rob, I'm pretty sure it's coming from you, or it could be Palin, of course. But at any rate, thanks for both of you muting. Great talk. I am fascinated by getting more of these complex algorithms down to the trigger. Are there any constraints on the complexity of this algorithm as it heads towards the trigger? Like, are you trying to fit it into the hardware level, or is it going to go into the HLT level?
I think, yeah, I believe there will be some restriction because it's on FPGA and
Okay, it is FPGA, so it's down at the hardware level. All right. Yeah, I'm really looking forward to seeing, because our group is getting involved in something similar, but not for tracks, of course, but really looking forward to see how this project evolves. Thanks.
Thank you.
Any other questions for Peilin? No? All right. Thank you. Nice talk. The next up, we had one cancellation. The fellow was not feeling well today, so unfortunately. Next up is David Lay. Lai?
Yep.
Want to go ahead and share your screen?
Okay. My project is the full name is the validating fast and tools against the ACTS framework. My mentor are Rocky and Charles. So introductions is that I'm a master students at University of Oregon. My project basically is the compare the tracking performance using the current tool is the ACTS, which is a heavy loaded full simulations software, where the tracking resolution calculator is one of the fast analytical estimator, which is lightweight and quick written in Python. So the goal is to validate if this tool is actually working, to compare with the actual SDTS framework, and using the model with the open data detector model, just relatively simple ones. The vision is that we will have a fast and reliable tool approximate the tracking resolutions in comparison with the full simulations results. So the project workflow is pretty clear. Is that this line is the HTS framework. You put into that with the ODD model geometry. Then you have the tracking performance matrix from HTS. In parallel, we are inputting the same ODD geometry into the tracking resolutions calculator, and we compare the performance plot of the five tracking parameters. Then until then, we can see a optimal agreement between the two. That would be the goal. So currently, what is working is that the ACT is fully installed and the OTT chain is fully running. And plus some initial ACTS performance plus versus the PT value. Then I extracted the ODT geometry from ACTS XML file and converted into the text file that is required for the tracking resolution calculator. So what's next is that even though I extracted, but we do need to verify if the geometry is consistent due to our inconsistency with our performance plot between the two. So that need to be verified. So then is finalize the comparison between the in the performance plot with the simple runs. For example, there's one particle, one vertex, and the fixed eta and the fixed PT value, and then start from simple, then being more complicated. Any questions, comments?
Anyone have any questions? All right, thank you for the talk. Next up is Andrii. Sorry, Andrii Len.
Yeah, hello.
Hi. Go ahead and share your screen.
Yeah. So can you see it?
Yes, we can see it now.
Okay. Hello, my name is Andrii Len. I'm from Taras Shevchenko National University of Kyiv. And today I want to present the project which I am doing as a part of IRIS-HEP Summer Fellowship. My mentor is Dmytro Kovalsky from MIT and CERN, and the project is called Mitigating the Impact of Simulation Mismodeling on DNN Training, Building Robust DNNs in the Presence of Detector Mismodeling. Our project is built around CMS short-term mu analysis, and in order to increase sensitivity for this insanely rare decay, we need to significantly reject combinatorial background. In order to do that, we started using machine learning, and so far we trained some simple, straightforward models which were using signal events from Monte Carlo simulation against combinatorial background events from real data. And this approach proved to be not very good. The problem with this approach was that the models were, to a large extent, learning to separate Monte Carlo and real data rather than just separating signal and background. That's why we came up with an idea for this project, in which we will compare two approaches. First one is to exclude Monte Carlo events from the training and train real data versus real data only, which we suppose will mitigate the influence of mismodeling on the training. And the second approach is to keep using both Monte Carlo and real data, but adjust the loss function to prevent the models from learning differences in domains. Here is general information on the selections we applied on the data gathering stage and features we are using for training our models. Overall, we have like 10 million events of real data and 1 million events of Monte Carlo simulated data. Here is a visualization of the mismodeling problem which we faced with our straightforward Monte Carlo versus data models. We can see that after we applied these models, distributions of some features are clearly different, and also mismodeling corrections required in order to compensate for such mismodeling are very high, as you can see in the last column of this table. The perfect case scenario would be a correction 1, but as you can see, these numbers are very far from 1. So in order to get lesser mismodeling, we decided to try different approach. First approach we already started working on is real data versus real data. We are lucky to have such a huge signal-like background in our spectrum, from K-short to pi to 2 millions to neutrinos decay. So we can use this peak as a signal region, and as combinatorial background regions, we can use these side bands from the spectrum. So far, we trained several models, and this approach instantly showed up to be very promising, but we faced several problems. For example, as you can see on this plot, our models were sculpting mass of a signal peak. As you can see, this peak is visibly sculpted by DNN predictions, which we obviously don't want to see. We don't want our models to rely on mass while making decisions. So to prevent this, we decided to try adjust the loss function by adding a new part to it to ensure that the model's output does not have any correlation with fitted mass. And the picture became much better. We hardly can see any correlation with mass, which is very good. So now we only need to find an optimal training configuration, taking into account this new part of the loss function. Regarding current status and our further goals, we already made a progress on the first approach called real data versus real data, and currently trying to find an optimal training with adjusted loss function. Regarding second approach, which uses both Monte Carlo and real data, we are currently studying the differences between Monte Carlo and real data in order to understand how to prevent these models from learning these differences. And also we are searching and reading articles which already performed something similar, like domain adaptation studies by David Walter. And after these studies, we will try to correctly adjust the loss function to mitigate the impact of simulation mismodeling. And our final goal will be to compare these two promising approaches and potentially use these models to improve overall sensitivity of the short-term analysis. Thank you for your attention.
Thank you, Andrii. Gordon.
Andrii, fantastic talk. This problem of dealing with MC and real data hits close to home for me. Physics analysis we published a little while ago. We had this problem where with the training, one of our data sets was only available in Monte Carlo, one of the training sources, and another training source is only available in data. And it took us quite a while to deal with, I think, a very similar problem. What we did in the end was we created a adversary that looks at a control sample which contains the differences between data and Monte Carlo, and basically punished the selection network for learning those differences. This is all published work, and so it's pretty, it's coming from Atlas, but it's pretty easy to go read. And it's a fairly simple, the idea behind it is fairly simple. But if you want, just send me something on the IRIS-HEP Slack. My name's Gordon Watts, so you can just find me on the IRIS-HEP Slack, and I can point you to some of the papers which talk about how the neural net was designed.
Oh, thank you a lot. I think it will be very useful. I will write to you. Okay.
Yeah, perfect. Thanks. A great talk.
All right. Thank you, Gordon. Anyone else have a question for Andrii? All right. Thank you, Andrii. Up next is Oleksii. Oleksii, sorry.
Yes, can you hear me?
Yeah, we can hear you.
Moment. There we go. Okay, my name is Oleksii Hrechykha. I'm a second-year master student in applied physics at Kyiv Academic University, and this year I'm continuing the work I've done last year on array API library completion under the supervision of Jana Osborne of Princeton University. And first of all, I would need to briefly introduce you to the necessity for such a library, and it arises simply in any experiment on a Large Hadron Collider you could think of, because basically every event doesn't have a fixed output and fixed numbers of particles and their types, which we could expect during each event, and therefore jagged or ragged arrays arise there because these are not numpy arrays, but rather the arrays which have various length and numbers of elements and degrees of nestedness, so to speak. And usually these arrays are handled by awkward array library, which is very fast and memory efficient and basically does what NumPy does as compared to Python, except for ragged arrays. However, the problem with this library is that it allows for arbitrary data, which is useful on its own, but limits the possible applications of a library because it's too general, and for high energy physics purposes you don't want to have an array which has arbitrary data types inside one array and work with it. It's not what is usually done, and therefore but the community has introduced the agreed upon standards for libraries working with arrays, which basically allow any user to expect certain things and the same or roughly the same functions and functionality, which is standardized and easy to use for anyone. And awkward array, due to how general it is, cannot possibly be API compliant, and therefore it's important to introduce a library which would allow to work with jagged arrays, but also doing that in a manner that is consistent with the array API standards. And ragged array library is basically like that. So it takes a jagged array, but then allows you to work with it. It's a wrap around awkward, which limits awkward's functionality, but at the same time conforms to the API. And my work on the project is completing the unimplemented functions, which are array manipulation functions, some array object functions, and linear algebra functions. The list of them you could see here, and the work has already been started, and basically the pipeline is to try out a function which solves the problem that API poses, do tests, and then either improve the function if the tests fail, or improve the calculation efficiency of a function once everything is done and well. This is basically it. Thank you. With that, I will be taking any questions.
Thank you, Oleksii. Any questions? All right. Thank you. Nice talk.
Thank you.
Hannah, you're up next. Do we lose Hannah? Okay. I guess we lost Hannah. She was here. We'll come back. Jack?
Yeah, I can present.
Yeah, if you wouldn't mind, go ahead and share your screen.
Yeah. There we go. All right. I can start?
Yeah, go right ahead.
All right, thank you. All right. Hello. My name is Jack Rodgers, and I'm going to be presenting on the project I'm working on for IRIS-HEP this summer, One Flow to Unfold Them All. And I am mentored by Massimiliano Galli. So just a little about me. I graduated this May from the physics undergraduate program at Purdue University, and I will be returning there to pursue a PhD in the fall. I worked for 2 years in Professor Mian Lu's research crew on high energy physics machine learning applications. And this summer, I am working on normalizing flows research for unfolding under Massimiliano Galli and the rest of his group. So, what is unfolding? So, in the detector, we have a limited precision and resolution. Of course, I'm talking about the detector and the LHC. And unfolding is the process of just correcting the observables that we reconstruct with the detector and our limited resolution and precision to get the true particle level observables. And these can be, whatever particles we are focused on. So this is kind of a really non-trivial problem, and it's also important for virtually all LHC analyses. And so, yeah, what is our approach? Our approach is to use normalizing flows. So earlier on, this problem was kind of modeled by just a response matrix and kind of just a linear reweighting of your reconstructed features to get your truth. But we are introducing normalizing flows for nonlinear yet invertible. Invertible will be very important. Mapping from reconstructed data to the truth observables. So we could see we could just take a simple distribution that we sample from and apply successive transformations to get an arbitrarily complex distribution. So the methodology we use is that we pass features, represented by Z here, with a binary conditioning variable, which represents which distribution space to map to. So we can have two successive mappings here represented by our binary conditioning variable, which are simulation of base and base to data. And obviously, since the function is invertible, we can go the other way as well. And we can compose both of these mappings to give one invertible mapping. So our simulation data or RICO level data to particle level. And that is the ultimate goal of this project, is to develop a unfolding framework for a single autoregressive normalizing flow and using a Boolean variable as a condition. And this would be cheap, efficient, and kind of most importantly nowadays, interpretable, since the functions are invertible. So this is just a little plot to show you baseline performance that we have so far just on Z-jets, about 1 million events. We can see that I've plotted transverse momentum and the mass of our leading jet. And we can see that, especially in mass of leading jets, we perform significantly better than our RICO variables. So this, yeah, just kind of shows like we'd have something that represents a particle, or I guess kind of comes out of a particle called a jet. This is what the detector observes. We can, kind of remap this. We can morph this distribution to get our particle level masses. So the first problem that I worked on this project was something called event displacement. And so event displacement kind of comes from the downside, I guess. It's a downside of using distribution level sampling and distribution level loss, which is that individual observables, like individual samples, are likely to be displaced from their gen counterparts, right? So if you look at this RICO to gen response matrix, you can see that you have some off diagonal terms here, but then when we unfold, these terms aren't present. They are absorbed into the diagonal. They end up in a separate bin, i.e. they are displaced into a different bin. And so we want to know, okay, like, can we solve this? How would we go about that? Naturally, you want to add another loss term, right? So we attempted to mitigate this with MDMM, the modified differential multiplier method. And it's similar to treating the objective as a constrained Lagrangian, where your Lagrange multipliers are continually adjusted by differentially modifying objective terms, i.e. via gradient descent, to account for constraints. The results from our MDMM tuning show that there is kind of an incompatibility between distribution level KL divergence loss and our MSE regularization term. Our best performance was attained when MDMM contribution to our loss was minimized. These plots show your L2 loss, your L2 norm, which is just MSE, versus the steps, so over time. And we can see that our green MDMM never really does better than our best baseline. So this is kind of not very surprising since they're two completely different objectives. One's a distribution level loss and one is a per sample loss. And then so the next thing I worked on was testing negative weights in a TTH next leading order Monte Carlo sample. So data from Monte Carlo methods is often weighted such that important and rare events can be given greater significance, so we don't have to generate a huge amount of samples just to get a decent amount of important events, so we weight them. These weights can be negative due to overlap of multiple different corrections. So you can correct for electro weak, you can correct for next leading order, you can correct for trigger efficiency. And we performed a sanity check on method correctness, even with the presence of negative weights, which can obstruct many other methods, can really, I guess, confuse your learnable function. But in this case, we see that our our distribution morphing is still preserved, and we still get decent performance out of this TTH-NLO sample. So the final thing is continuous flow matching, which is what we're working on right now. Continuous flow matching is really interesting. It's finding a multi-dimensional velocity field. In this GIF, it's 2 dimensions, clearly. But you can have as many dimensions as you have features. So you give the path that a sample takes from one distribution to another. So we start out with some, randomly scattered distribution, and we can these points can just flow along our velocity field to another distribution. And so we train on samples at different times. These times are from 0 to 1, 0 being the original distribution and 1 to the final distribution. And we just learn this velocity field and then integrate over it. Yeah, and the velocity field is learnable, uses a multi-layer perceptron. You could use any really learnable function. This is just what we choose for simplicity. And so we have conducted our first preliminary demonstration of conditional flow matching with Z-jets. If you look at this plot or the left plot, you'll see that there's a slight shift. These are normalized, but there is a slight shift in taking our Rico and then going to Gen. And yeah, it looks promising as you can see from the right plot. We're kind of more or less getting unfolding or decent performance better than Rico. We do need to scale this up and apply more advanced techniques, but so far the results look promising. Thank you. Yeah, questions, comments, concerns?
Thank you, Jack. Jordan.
Hi, it's nice to see this. I'm trying to understand the slight methodology difference here between this implementation and what OmniFold is doing right now. Have you been in talks with anybody from the deep learning HEP community to maybe give a talk on this there and see what their opinions are? Because right now I think these are two different things that are relying on normalizing flows.
Yeah, so to answer your question, no, we haven't really given any talks so far, I don't believe, during my time here. What is I mean, OmniFold is a little different in that you're taking I believe the original implementation is taking classification weights and using those as weights, and they are learnable, right? These classification weights, but it's not per se distribution morphing, like on the distribution level. It's more of just reweighting with the learnable function. Does that?
Yeah, I think this is kind of what I was trying to get at. It's not clear to me what the difference is between just a morphing versus a reweighting when you talk about distributions.
Yeah, I mean, ultimately, I think it's more of a semantic thing, honestly. I mean, yeah, we're using normalizing flows and we're applying a distribution level loss, right? The loss that we apply is like a KL divergence, right? It's over the whole distribution. Whereas something on Omnifold would be like a per sample classification, right? Something like a BCE loss, like binary cross entropy per sample. Yeah, I would say that's the main difference.
Yeah, I see now. Okay.
So if I can just interject 1 second, everything that Jack said is perfectly correct. Just one other thing to add. The main idea is that, let's say, the difference between reweighting and morphing is that when you reweight, you are essentially learning different ways to make the distributions look the same. When you morph, it's actually effectively a correction. So you are effectively, let's say, moving the event from, let's say, one bin to another. That's pretty much the idea. But everything else that came before was correct. Just to add another part.
All right. Thank you. Any other questions for Jack? Okay. Next up is Hannah, who's now reconnected.
Okay. Should I be sharing my screen or is it?
No, go ahead and share your screen.
Okay, no problem. One moment, it's kind of giving me an issue right now.
No worries. Do you want us to come back, Hannah?
I think I got it. It's just
All right, no
okay
worries.
from beginning. Okay. Yeah, sorry about that.
No worries. Here you go.
All right. Yeah, so my project is HS3 Support for Combine, and my name is Hannah Havel. I'm from Northern Illinois University, and my mentors are Massimiliano Gali and Nick Smith. So yeah, like I said before, I'm an incoming senior at Northern Illinois University, studying both computer science and mathematics. My research interests are in computational physics, data science, scientific computing, such as machine learning, and quantum computing. And I started last week, Monday, so I've only been working for about a week, right? So as a project overview, Combine is CMS's standard statistical inference tool. And to talk about how Combine currently works, the format uses binary root files to store statistical models in workspaces, and models are defined using data cards. And currently, binary formats are hard to share, inspect, or modify, and they require root, which is a data analysis framework to interact with different data cards. And this is an issue because it limits interoperability with external tools or non-CMS workflows. And then here I have an example of a data card. So data cards are essentially the text input describing the model, whereas a root workspace is the binary file produced from data cards that Combine uses internally. So this is the current format for data cards used in Combine. HS3 is the higher energy physics statistics serialization standard, which is human and machine readable JSON-based format. And this enables easier model sharing, versioning, and publishing, and is easier to integrate with modern data science tools. So my goal is to integrate HS3 into Combine using an approach that involves introducing compatibility step by step, so incremental testing of JSON compatibility. And then this is sort of pseudocode for what that JSON format may look like. So this is both human and machine readable, and this is what I intend to integrate into Combine. So to summarize the motivation, right now binary root workspaces are difficult to inspect, debug, or share, and this may require specialized software to modify between different persons. But the JSON format is standardized, accessible, and promotes sharing and publishing of models. And adopting HS3 will modernize the workflow and reduce reliance on legacy components within Combine. So yeah, essentially HS3 solves this by using a standardized JSON format, which makes statistical models easier to publish, share, and integrate with other tools. And legacy Combine components, especially custom classes that complicate reuse across platforms, adopting HS3 reduces reliance on those. So far, 1 week progress. I have done some exercises and additional reading to become familiar with Combine and data cards. On my own Alex Plus environment, I set up the Combine build environment, and then reviewed and tested some recent updates that enabled JSON HS3 support and statistical modeling tools. So as we transition to what's called the hybrid approach, which is essentially sort of incremental step-by-step replacement of binary components with JSON-based equivalents. And this will maintain some of the original structure that's currently used in Combine. And this will be done by starting with simple data cards with text, and then building them up in complexity by introducing shapes and different types of data cards. So I will run data card tests with HS3 pointers, and then identify missing model components that facilitate the reading and writing into Combine. And then if time, we will aim for a full approach, which is essentially the ability to fully read and run from JSON files alone. And then that is it.
Thank you, Hannah. A nice talk despite having started just a week ago, so no worries.
Thank you.
Jordan, did you have your hand raised?
Yes, I'm actually excited to see this, and I'm kind of hoping for a little bit of clarification because I come from Atlas, but I don't really use. I mean, I've used CMS Combine, but I'm not familiar with the underlying code. But so I'm hoping you can correct my understanding. In CMS Combine, I thought that anything that is done is kind of a layer on top of a Woo workspace, which means that fundamentally anything you build in Combine is just a Woo workspace under the hood. So do you not just rely on root to export l.tracer, or what's the missing piece here that makes it hard for Combine to adopt HS3 out of the box already?
Anna, I can take this if you want because you started last week, so I don't expect.
Oh, sure. I mean, I can make an attempt. So
Absolutely,
yeah,
then go.
okay. Yeah, so yeah, you're right. From my understanding, everything like in CMS Combine, everything eventually gets converted into a root workspace. But I guess what's missing in HS3 for making that easier is that they also include like custom combine objects, which is used to like import and export uh from to and from JSON. So there's just some importer and exporter logic that needs to be changed. And if we do like what I call the what we're calling the hybrid approach, that in order to adjust that logic to work with HS3, the changes to the code are going to be minimized, but where a full approach is going to require some additional code. So I guess yeah, that's probably my best shot at that question.
Yeah, that's absolutely 100% true. Moreover, there is also, let's say, inside Combine, every time that we create the workspace under the hoods, there are also other, let's say, parts within the code that are mostly borrowed from root stats and other root classes. That it's essentially makes it a bit tricky to find exactly all the places where we have to change code in order to let's say provide let's say the full approach, the full compatibility with HS3 would mostly is a bit tricky because of, let's say, how the code is made inside, let's say, under the hoods. Let's put it like this, and it requires also some digging. Yeah, but in principle, with the hybrid approach, it's a bit more easy, meaning that what we do essentially is just setting up in a way that the data card, instead of pointing to the root or the root file or the root workspace, points to a JSON file. And essentially, the idea is that by doing this, let's say it's not a full HS3 compatibility, but already we fixed two problems, which is what Anna said before. So the backward compatibility between versions of root and roofit, and also that we would not have to publish binary files essentially, because now in Combine what we're doing is publishing the data card plus the root files and the roofit workspaces. So this is the, let's say, the reason behind going step by step and first trying to achieve the hybrid approach and then going for the full one. I don't know if this answered the question.
Somewhat. Are you planning on changing anything about the Combine data card, or are you just providing an additional input-output that supports the JSON format that's compatible with the HS3 specification.
So the thing is that for backwards compatibility with literally everything that was done so far since the discovery of the Higgs, we need to maintain data cards. So the idea, the project would be to also in this case go step by step. So basically having the HS3 compatibility as an additional way to describe the models and the inputs to combine, and then see where to go from there. For many reasons, we cannot go immediately with, okay, we provided full HS3 compatibility. From now on, we will only deal with JSON files. It's not something that will work in the collaboration.
Okay.
So the idea is to, yeah.
Okay. Any other questions for Hannah? All right, thank you, Hannah. Up next is Mykyta.
Mykyta, actually, yeah.
Sorry, thanks.
Yeah, okay, it's okay. I cannot share. Okay, yeah, thank you. So can you see my screen?
Yes.
Okay. So hi, I'm Mykyta. I am graduated half year ago as a master's degree in the Kyiv Polytechnic Institute in Institute Applied and System Analysis, and today I will show you the project with the thematic packaging HEP tools for conda-forge with mentor Matthew Fickert. What's the main purpose and the point of this project? The physics simulations and all these tools and analysis is some kind really difficult sometimes to run because it requires from scientists for students to knowledge how to build with the CMake, how exactly it compiles, which dependencies they should install, and sometimes they just really struggling because they don't have this technical knowledge how to do that. So the purpose of this project is to create much easier tools just for one command, and you're ready to go with your simulation process and analyzing some data. In this project, it was used by tools conda-forge. The conda-forge is a community-driven tool for packaging some binaries, utilities, etc. It provides a really flexibility to integrate for different architectures, for different platforms, and because, for example, some specific tools need to require some other packages which is not required in, for example, Windows or Linux. And also conda-forge provides a community cyber infrastructure for building tools. It's just for more comfortable creating building tools and for more easier integration packages in the conda-forge. And also there is several ways to apply packages into conda-forge, and one of them is a Rappler build. The Rappler build is a new one, is written on Rust. So it's really fast and it's really new one, and it's also updating really recently, so really fast. And also it provides a really comfortable configuring packages in recipe.yaml, which is really readable and pretty understanding what exactly is this tools should be using, and also you can specify which tools and which commands should be run, for example, for tests, for buildings, for different architectures, for different operating systems, and so on. So during this project, I also learned how to use how to apply this by using how to apply package into conda-forge acts in the HEP community, which is really used in the HEP community. I've seen before that in this presentation that about acts. So also I'll be able to run it on Apple Silicon and Linux systems. And so my plan for this project is also to contribute to add more packages from this HEP packaging coordination that they actually are not implemented in the conda-forge package. So for much easier use it for installing them on Linux and macOS systems. So I guess that's all I can say you. So, any questions?
Thank you. Any questions?
I guess no, it's pretty simple and straightforward project. So
that's fine. That's all projects contribute in some way. So that's all we have for today, everyone. So thank you all for coming. Thank you to all the fellows for their talks. We appreciate it. Hope to see you all again soon. That's it. Bye.
Thanks, everybody.
Bye.
bye.
Thank you. Bye.
Bye.